So first of all, EDM. It's not dance music, it's electric discharge machining. Wire EDM, that can really cut out arbitrary shapes very easily. And it cuts almost like a bandsaw. If a bandsaw didn't cut, I've wanted to make a wire EDM for the longest time because it's like the holy grail of machine tools. Specifically, wire EDM is so hard because you have this super thin wire, and if anything happens to that stupid wire, it's going to break. If it has too much spark energy, it's going to break. If it has too little, it's going to touch the workpiece and then it's going to break. If there's not enough flushing, it's going to short through the dielectric and it's going to break. And if it vibrates at all, it's going to touch the workpiece and then that's going to short it and it's going to break. There's just so many ways that this wire can break. So there is a channel out there that attempted something very similar to what I'm doing. Action Box. They tried to make a wire EDM, but it didn't work. And I actually figured out through my wire EDM exactly why theirs didn't work. So I'm going to go over that a bit later. But hopefully they can get theirs up and running. That would be super cool. I saw that the power supplies were going to be $3,000, and I knew that wasn't going to happen with my budget. So I thought about why, and I realized it's because they have such high power output. And I knew one other thing that had such high power output, and that is
LiPo batteries.
So I went to designing a board. So this is the board that I landed on. It uses 4 300 amp MOSFETs because why not? They are cheap electronic components. And it uses 4 current sense resistors with 2 different monitoring ICs that I never used. And then it uses, I think, like 20 service mount capacitors with room for more in the back. It uses these big bus bars, which essentially the LiPo will be attached here, and then the gate drive voltage is attached up here to the 10 volt. So this is the final board, all built up. Okay, so here is the overall mechanical design. First up, we have the wire coming in from the top, and then it's going to wrap around these cap stands, and then it is going to go over the load cell pulley, down through the first nozzle, through the second nozzle, and then it's going to wrap all the way around back up to the stepper motor. So this stepper motor up at the top is going to be pulling at a constant velocity. And this O drive over here is going to be in torque control mode, and it's going to be applying a constant torque to that capstan, and it's going to be acting as a brake. So overall, this system has a constant velocity and a constant tension in this wire. And this load cell can be used for closed loop tension control mode, but I never actually got around to doing that. And this is set up as a dual capstan mechanism because it adds a lot of friction. And it also is bending the wire both ways such that it's not biased very much coming out of the load cell pulley. And on the top and bottom, you can see these 2 caps, which is where dielectric gets shot up out of, which is used to flush the cutting area of any chips or debris. So this is the nozzle assembly with the cap removed. And this is just a $7 nozzle off of McMaster that happened to just fit this wire very nicely. So the nozzle threads into here, and then this is the cap that goes on it. So the wire is coming down from the top all the way through. Then we have dielectric being pumped in through this left side port. And this port is just for wires if I wanted the contactor to be right at the nozzle, which I didn't end up doing, so I just plugged this up. Yeah, and as you can see, this was made to be printed on an SLS printer, which is why there's all this complex internal geometry, which I was lucky enough to have access to in my internship. This could be designed for other types of 3D printing like resin or maybe even FDM. Now for a quick overview. So in the top left, you can see the stepper drivers along with the power supply for that. And then in the middle is the O drive. On the right side is my board with the LiPo batteries, and there's tons of probes connected to that. So here's the actual wire EDM with its nasty vegetable oil bath. And you can see it's just mounted on a single axis. This is just because I just wanted to test. This axis is actually just the axis from a Form 3L printer.
No. Oh my god. Oh! Let's go!
So after I'd done all my testing, I had my parameters very dialed in, but it still wasn't working right. Somewhere in the electrical system, there's something going wrong. So the way I had this set up is that the negative lead was connected to the ball bearing, which had the wire running over it, and then the other end was connected to the workpiece. So turns out running current from the inner race of a ball bearing to the outer race is not reliable at all, and especially when you're running kilohertz ranges, it's going to miss pulses, kind of like switch debouncing. Time the ball bearings are rotating around, they could be breaking or gaining electrical contact, and so I actually ripped that out for this. This is just a lead screw nut, and this fixed a lot of issues, and I'm going to show you the result of that.
Oh my god. Dude! Let's get.
So this right here is the result of the cut. This little slit right here, and it doesn't look like much, but this does show a maintained spark, and it also shows that the flushing wasn't anywhere near enough. You can see this massive black cloud forming. This is all the chips, and also you can see that this pump is super weak. And so when the wire got all the way in here, there was so much metal chips that it caused it to short and the wire to break. So next steps would be to install something like a real pressure washer instead of just a $30 portable Amazon pump. So I really hope you enjoyed watching this video, and I did open source all the files. The links are in the description. I'm hoping that if somebody else is inspired by this, you guys can take these ideas and apply it to your own designs.